far apart. Okay. Good?
It pulled.
Cool. Oh my god. Okay, so our project starts by connecting those two gates, and then that will start our tracked vehicle, which pulls down and makes that weight fall over, and then that's connected to this string, which is going to trigger our catapult, which will then pull off this paper clip, which is going to be attached in there, and when that paper clip gets pulled off, that will release the water from the funnel. So when this paper clip is pulled off, that shows the effects of friction because the coefficient of friction between the metal and the rubber is very high, and so it takes quite a lot of force by the catapult to pull it off. And this amount of friction also depends on how much tubing is in the clip. The more tubing we put in it, the harder it is for the catapult to pull off. And then our catapult, as it's pulling on the string, shows conservation of energy. So when the triggering mechanism is attached, like this, then the catapult only has gravitational potential energy because it is not moving, but as it is released, the potential energy is converted into kinetic energy, causing the catapult to move, which eventually pulls on the paper clip and the pipe. So energy, therefore, is not lost, but instead conserved through our catapult. Alright, so once the water is released, it goes into this piping system, and then it ends up going into this cup. And when the cup is full, this goes down to control and close the circuit for our propeller car. And then the water will drain out into here, and then that will open back up the circuit again. So our teeter-totter uses Newton's third law, which states that every action will have an equal and opposite reaction. As the water is flowing into the cup, it puts a force on the elevated end of the teeter-totter, and this force causes the elevated end to go down, like this. And since the teeter-totter's normal force is less than the force of the water, the elevated end is lowered and hits the ground. And so this change in position is an example of the equal and opposite force of the water. Alright, so momentum can be seen in our project in the collision between the smaller marble and the larger marble, which will happen right here. So after the smaller marble has left the plastic tubing, it has a specific amount of momentum that it has required because of the increasing velocity as it moves down the marble run, and this momentum is conserved in the collision, and then the larger marble will begin to roll. And then Newton's first law can be seen when the larger marble hits the propeller car. So the propeller car is at first at rest, but then the external force of the large marble hitting it makes it move. The final law that can be seen in our project is Newton's second law, and this can be seen with the Ferris wheel when it hits the hockey puck. The Ferris wheel exerts a force on the hockey puck using this kind of mechanism that we've built, and that causes the hockey puck to roll. And so this force is equal to the mass of the hockey puck and its times its resulting acceleration. So once our propeller car, or our hovercraft, sorry, is turned on, then it will hit this marble, and this marble will go into this tubing and then go all the way down, and then it will hit that marble right there, which will then go on to hit our propeller car, which will unblock the optics sensor, start this Ferris wheel, and then the Ferris wheel, using this cup right here, is going to spin around and knock down our hockey puck in order to end our project. And then we have a little mechanism here that the string will wrap around and then eventually pull that sensor away to stop the Ferris wheel and then officially end our project.